Now we are at the end of time-dependent perturbation theory. This is the last lecture for the time-dependent perturbation theory. In summary, we studied this S matrix, which is a time-ordered exponential of integrated potential in the interaction picture. Interaction picture potential is expressed as in terms of the potential in the Schrödinger picture multiplied by the unperturbed Hamiltonian's time evolution operator. And this time-ordered product can be expressed in terms of theta functions, and theta function can be expressed as an integral from minus infinity to plus infinity as this kind of complex integrand. When we express this S matrix in powers of potential, it can be made a series expansion. And if we sandwich this S matrix with the initial and final state, we obtain the transition amplitude AFI. Again, transition amplitude AFI can be expressed as in perturbation theory as a series expansion in powers of the potential. The final result in the previous class was that the zeroth order transition amplitude is just one that does not interact. An nth order expression for the transition amplitude AFI was simplified into this form: 2 pi delta function of the energy conservation between the initial and the final state, and multiplied by a matrix element M, IM. And this matrix element can be expressed in powers of V again, and at the first order in V, it is just minus I potential in the Schrödinger picture sandwiched by the initial and final state. From second order, we have strange factor that is called the propagator. That propagator, origin of the propagator is the theta function that orders the flow of time. So, in short, we can express that propagator as I over energy. That energy is the same as the initial and final state energy subtracted by unperturbed Hamiltonian plus I epsilon. So this is for the theta function. And at the end, at both ends, we have minus I potential in the Schrödinger picture. If we expand this by including states, just one, that is one. If I include this, that I would find, because this is a number, pure number, and this is a Hamiltonian, so unperturbed Hamiltonian, and the state n is eigenstate of the unperturbed Hamiltonian. So they are expressed in terms of the energy of the intermediate state. And during the calculation, we find that there's energy delta function whose argument was E minus, open the parenthesis, EF minus EN, something like that. And the other delta function has this kind of form. And here, energy of the nth state does not care about the energy conservation between the initial and final state. Therefore, it is possible to have energies in the intermediate state that may be different from the initial or final state. So in the intermediate state, that is also called a virtual state, energy conservation may not work. Okay? This is related to uncertainty principle. If the energy is intermediate energy is different from the original energy, that is initial or final state energy, but because the product of delta E and delta T is finite or greater than finite value h bar. Therefore, if the energy difference is small in comparison with initial or final energy, if it is small, it can stay longer. And if they are different, then, for example, EI and EN are very much different from each other, then it cannot stay longer. So the intermediate state does not stay long, and we cannot detect the intermediate state at all. All right. This method can be extended to higher orders. For example, if I have 3 powers in V, then both ends we have potential. And we just put these propagators. Okay. Therefore, in general, transition amplitude at order n can be expressed as at order 0, it is minus I potential only. From order v squared or higher, we attach this vector again and again and again. If we want to express in terms of states, intermediate states, what we have to do is just insert this kind of complete states as an identity in here. Okay? That is again and again and again. All right. So, although the computation is a little bit complicated, but repeated structure can be read up and summarized as the Feynman rules. First of all, transition amplitude at order 0 is 1. From order 1 to higher order, we always have the energy conservation delta function between the initial and final state. So 2 pi delta function and something. And that something is called the transition amplitude, matrix element M. And matrix element M at order n can be expressed in such a way that the first term has minus IV's potential, and from second order or higher, we just multiply minus I potential times the propagator. We call this minus IV potential in the Schrödinger picture to be the vertex vector. And this is called by the propagator. Originally, that came from the theta function that describes the time-ordered product. If we want to compute the transition rate gamma is the square of the transition amplitude divided by interaction time. And because the transition amplitude has 2 pi delta function in here, when we square it and divide it by time t, we already have derived that it is just a 2 pi over h bar single delta function multiplied by matrix element squared. In perturbation theory, we can express this sky in powers in V, and it can be expanded in such a way. At order 2 V squared, our result will be this energy momentum delta function and order 1 matrix element squared. And at order 3, we have second order times second order matrix element times first order 1, and so on. Second order and first order as amplitude and its complex conjugates, and so on. So we have constructed a simple way to describe, to calculate interaction that is localized within some time And from the state in the unperturbed state to the final state, which is also unperturbed state. So this is called the time-dependent perturbation theory, and the Feynman rules simplify all of the complicated steps of calculation. Thank you.